Hi and welcome to video 6 on my video series on graphs and graph theories. And here's the learning goal, and today we're going to talk about Hamiltonian graphs, which is only a small step on from Eulerian graphs, and these are called the traveller problem graphs. In a Hamiltonian graph, we're looking to visit each vertex. So whereas an Eulerian graph is about visiting each edge, the edges are important, they relate to trails. In a Hamiltonian graph, we're trying to visit each vertex exactly once without repeating any edges. So this is called, this is to do with paths more than trails. So here's some definitions. A Hamiltonian path is a path that visits every vertex of a graph only once without using an edge more than once. If it starts and finishes at the same vertex, then it's also a cycle. Hence, it's called a Hamiltonian cycle. If a graph has a Hamiltonian cycle, then it's called a Hamiltonian graph. It's important to recognize here that if a graph has a Hamiltonian cycle, that means it starts and finishes at one vertex and goes through every other vertex. Well, that means it's got lots of Hamiltonian cycles, because you could start at a vertex from the middle and go through in a different direction. So it won't just have one Hamiltonian cycle in a Hamiltonian graph. If a graph has a Hamiltonian path, so it's open, but is not a Hamiltonian cycle, then it's called a semi-Hamiltonian graph, or just called semi-Hamiltonian. Let's have a look at an example. Define each of the following as either Hamiltonian graphs, semi-Hamiltonian graphs, or boring. I mean, neither. And I've written the answers there, but I think I actually ended up planning and getting it wrong. But let's have a look at this. Let's say I started at B. Can I travel to each vertex exactly once? And can I get back to the start doing it? So I get to A, I get to C, I get to E, I get to F, I get to D, I get to B. I've covered every vertex, I've not repeated an edge, and therefore this is a Hamiltonian graph. And I think I planned this one to be a semi-Hamiltonian graph, but I can actually do it using a Hamiltonian cycle. So I start at A, I go to H, I go to I, and this is an important strategy. I'm going from the outside in. B, then D, G, now I can go E, F, C, and back to A. And that actually starts and finishes at the same location A, and therefore it's a Hamiltonian graph as well. And I meant to say draw a graph that suits the missing option, but there are two missing options. So I might leave that to you to have a think about. Could you draw a semi-Hamiltonian graph, which I dismally failed at? Could you draw a graph that has neither Hamiltonian or semi-Hamiltonian traits? And I'll leave you with that. So here's the solution to the one that I suggested you do as homework last lesson. Hamiltonian graphs, solve it. This is the homework from last lesson, and there is a solution. It doesn't really matter which vertex I start on. If I start on this vertex, I do that, travel around this way, and I get back to it, or whatever. This is a really famous problem that comes up, and it's definitely a Hamiltonian graph. So, can you define Hamiltonian graphs and semi-Hamiltonian graphs? Can you determine the Hamiltonian paths or cycles? Can you apply these ideas in context? I hope so. And here's our work and the content detail. All the best.